Now I want to examine the case of heteroatom protons. They're an unusual bunch, these hydrogens that sit on atoms other than carbon. We find them in alcohols or in carboxylic acids or amines. Their chemical shifts are surprisingly broad and varied. They can be far downfield, but also surprisingly far upfield. From a strict electronegativity standpoint, it's sometimes surprising how far upfield they can be. After all, we would think that a hydrogen sitting on an oxygen or on a nitrogen, both highly electronegative atoms, should be quite de-shielded and appear downfield. And in fact, that is the case in many instances. Carboxylic acids, for example, often show the OH peak in a proton spectrum somewhere above 10 ppm, often all the way down to around 12 ppm or so. Water itself will show up at around 4.6 to 4.7 ppm. But interestingly, put water in a solvent like chloroform and you will actually find that the OH peak is around 1.6 to 1.7 ppm, depending upon what else is in the solution and the concentration. That is surprisingly far upfield. Now it is true, one doesn't often put water in chloroform, and in fact they are for the most part immiscible with each other. They don't dissolve in each other. But it is possible to have a trace of water in chloroform, a little bit to make the chloroform wet, or perhaps the sample that you're dissolving in the chloroform itself is a little bit wet. It may be that it's a product of a long synthesis and water was one of the solvents that was used in the previous step. Sure, you dried the sample, but it's unlikely you got every single water molecule out of there. As an illustration of what I'm talking about, consider here the proton spectrum of a fairly simple organic molecule, pentene. You see the alkene peaks in their expected positions at 5 or higher ppm, and you see the other three peaks down closer to 1 to 2 ppm. That methyl group certainly right there at 1 ppm, sort of like we would expect it. What I want you to focus on is this area here, right around 1.6 to 1.7 ppm. You have to zoom in on the baseline pretty far, but you see there is a broad little peak down here. That is a trace of water. Okay? This sample, this pentene sample, seems to be slightly wet. And in fact, this broad little peak around 1.6 is quite common in a lot of different samples. It's usually small enough that we ignore it. It's not something we get, all excited about when we see it. But it is an example of a trace contaminant showing up in the baseline of our spectrum. But it is interesting. Water, there it is at 1.6 ppm, quite a ways upfield. In fact, the water chemical shift is strongly dependent upon the nature of the solvent it's in, how polar that solvent is, and whether it's a good hydrogen bonder. I'm going to show you a few numbers from a reference paper that came out in the Journal of Organic Chemistry a little less than 20 years ago now, but it wasn't a groundbreaking research paper. What it was is a compilation of all the different positions that various molecules like water could have in all the different NMR solids, all common contaminants that are in there. And as such, it's a highly useful paper and very, you referenced many times. I reference it many times, and I even have a copy of it on the course website for your use as well. So I want you to, I pull out specifically three cases here. One, they show the chemical shift of water in benzene, in deuterated benzene. Now, you'll notice that it's given as around 0.4 ppm. My gosh, that is so upfield, it's approaching TMS territory now. But think about it. This is water sitting in benzene. Benzene itself is nonpolar. It is not a hydrogen bonder. I interpret it this way. This is a water molecule in a very hostile, quote unquote, environment. those hydrogens of water have nothing in their surroundings to be attracted to. So I consider those hydrogens essentially tight to the oxygen, very close to it, buried in its electron clouds. There is nothing in the solvent to pull them away. That's what gives it such an upfill chemical shift. But now consider the chemical shift of water in a solvent like acetone, around 2.8 ppm. It's considerably downfilled from the value we saw in benzene. It's not nearly 4 to 5 ppm. Acetone is a polar solvent, but it's not a good hydrogen bonder. I interpret it this way. We essentially now have water molecules in a somewhat more friendly environment. The hydrogens, instead of being tight to the oxygen and buried in its electron clouds, with the polar acetone molecules around it, are being pulled out a little bit, de-shielding them some. The last number that I'll call your attention to specifically is water and methanol. Now methanol. Now we have a very polar solvent, but also an excellent hydrogen bonder. Okay, it's much like water that way. Here the chemical shift is all the way down to almost 5 ppm. Same water molecule, but now appearing at 5 ppm. The surroundings of the water molecule, methanol, strongly polar, hydrogen bonding, those hydrogens on water are now being pulled quite a ways away from the oxygen atom itself and rendering them quite highly de-shielded. A clever illustration of the unique nature of heteroatom protons is the proton exchange reaction and something that I've called the D2O drop test. Look at the spectrum of a molecule. It's called propanol, and notice for a moment that it has chemical shifts pretty much where you'd expect them to be. There are the alkene hydrogens above 5, the CH2 group next to the oxygen at 4, and one other resonance that is likely to be the alcohol group, but it is down there around 2, kind of in a rather upfield position. The other thing about that particular peak is it does integrate a little bit on the high side, about 1.3 when you'd expect it to integrate around 1. Let's say for the sake of argument that this were an unknown molecule or something that you'd spend a lot of time synthesizing and you were really desperate to confirm that that resonance there at about 2 ppm was truly a hydrogen on an oxygen, was truly an alcohol. One thing you could do is take advantage of something called the hydrogen exchange reaction. So remember, whenever alcohols and water are together in solution, they are exchanging hydrogen atoms quite rapidly. The activation barriers to this process are very low, so this is a very rapid reaction. So I've illustrated it here by color coding one of the molecules, and the idea is simply the hydrogens are just trading places quite rapidly with each other. To take advantage of something like this and try to prove a resonance in a proton NMR spectrum is actually from a hydrogen on an oxygen or even on a nitrogen, one thing you can do is something called the D2O drop test. Take your NMR tube after you've run the spectrum, pull it out of the magnet, add a drop of D2O, just one, cap it back up and give it a couple of good shakes. What will happen is this hydrogen exchange reaction will now take place, but now it will take place with deuterium. And so you expect to see any hydrogens in your proton NMR sample that are heteroatom hydrogens to either vanish or certainly to shrink in magnitude. Mainly because now instead of hydrogens, you are exchanging deuteriums in your molecule. Now, the hydrogens that are attached to carbon, they're not going to do anything. They're going to completely ignore the D2O. But the heteroatom protons will exchange. And since now, instead of just hydrogen in place, they have deuterium, they are going to be invisible in a proton NMR spectrum. Certainly, deuterium is a magnetic nucleus, but not at 400 megahertz, it isn't. And so it's not going to appear in our spectra at all. To see this, look at the propanol spectrum again, but now look at the result of the D2O drop test. The second spectrum shows the exact same tube, exact same sample, but after shaking with a little bit of D2O, putting it back in the magnet. You see a couple of major changes. One, our suspected alcohol peak has indeed shrunk drastically. And so, therefore, many of those hydrogens have been exchanged for deuterium and vanished. We also see a new peak over here at around 4.6. This is water. And remember, water and chloroform don't mix very well together. There's actually a little bit of water clinging to the sides of the NMR tube and a little droplet of it near the top floating on the chloroform because it is less dense than chloroform. It's picked up a lot of hydrogens from exchange with the sample, and so we get this fairly large water peak. Here we are, water in water, down there at about 4.6 ppm. So to summarize, when you're thinking about heteroatom protons, there are a couple of things that you will notice as you run many spectra or look at many spectra. Heteroatom protons can vary considerably where their chemical shifts are. They are often broad in an NMR spectrum, often broader, wider peaks than hydrogen sitting on carbon, partly because of this hydrogen exchange process. They are exchangeable. I've seen some references refer to, these are exchangeable protons rather than the D2O drop test, but it means pretty much the same thing. In other words, if you are ever told that that signal at 2.5 ppm is exchangeable with D2O, that just means that those hydrogens are on a heteroatom, either part of an amine or part of an alcohol. Very often, heteroatom proton signals will integrate sometimes on the high side, not exactly, say, 1 that you might expect, partly because these types of samples are very often wet. They have picked up some water from the atmosphere, and that tends to boost the integration of alcohol and amine signals. It doesn't have to be a tremendous amount, but they will often integrate a little bit high.